In the last session, we had looked at definition of 2,4 trees, which is a special type of a multi-way search tree. We had seen that a 2,4 tree which is going to store n items will have height of order log n. We also had seen how to query in a 2,4 tree. As in AVL tree, 2,4 tree are generalizations of binary search tree. So, in this session, we look at the edit operations on the 2,4 tree. The operations namely are insertion and deletion. So, let us look at insertion in a 2,4 tree. So, to make things simple, we will assume that the key that we are trying to insert is already not present in the tree. So, we are trying to insert a key which is not present in the tree. So, suppose we want to insert an item with a key k in a 2,4 tree. As in binary search tree or AVL tree, the first step is we will search for k in the tree. So, look at the example. We want to insert 115 in the 2,4 tree. So, the first step will be to search 115 in this tree. We also know that since the key is not present, it will end in an external node. So, that external node we are going to call as Z, and we are going to denote by V a parent of Z. So, the slide precisely shows V and Z. Once we identify V, we simply insert the key that we want to insert into V. So, 115 is inserted at location V, and we also add a new external node at V, which is called W. Now, insertion so done preserves the depth property, since we are just adding an external node at the last level. So, the depth property is satisfied. In this particular case, even the size property is satisfied. We see that at each precise node, 2,4 size property is satisfied. So, the resultant tree is a 2,4 tree. Now, this may not always happen. Let us try to insert 160 into the tree that we already have. So, procedure is similar. We start by searching for 160 into the tree. We know it will lead us to a external node. V is going to be the parent of that external node, and we are going to insert 160 at that node. Now, what we observe is that at V the size property is violated. In a 2,4 tree, you can store at most 3 elements at a node. In this case, at V, now we are storing 4 keys. This violates the size property of the 2,4 tree. This is called an overflow at V. The height property is satisfied. What is violated is the size property. So, we have to fix up this overflow, or the overflow has to be resolved. So, we will see how to resolve the overflow. So, we perform what is called a split operation. So, we look at the node at which the overflow has occurred, which has been marked as V. Since V has 4 keys in it, it will have 5 children, which are going to be the external nodes. We will name them V1, V2, V3, V4, V5. We also denote by K1, K2, K3, K4 the keys that are stored at V. So, V is the node where overflow has occurred. It has 4 keys, namely K1, K2, K3, K4, and it has 5 children, namely V1 to V5. To resolve the overflow, we do what is called a split operation. we replace V with two nodes called V prime and V double prime. V prime is a 3 node with children V1, V2, V3, storing keys K1 and K2. V double prime is a 2 node with children V4, V5, storing key K4. So, in our example, this is going to be V prime and this is going to be V double prime, and V prime is a 2 node with children V4, V5, storing key K4. So, if you look at this, so this is going to be V prime, this is going to be V double prime. V prime is going to save K1, K2, V double prime is going to save 160 key, that is K4. Their V1, V2, V3 are going to be children of V prime, and V4, V5 are going to be children of V double prime. The key 150 is going to be pushed to the parent of V, which is U. So, if V is a root, we are going to create a new root, or else we are going to let U be a parent of V. So, we are going to insert K into U and make V prime and V double prime as children of U. So, that if V was the ith child of U, then V prime and V double prime becomes ith and I plus 1th child of U. We see that one split operation takes a constant time. As a consequence of split operation on a node V, a new overflow may occur at the parent U of V. So, we see in this operation that once this split operation is performed, at this level the size property is satisfied, but it has been propagated one level up. Now, there is a overflow at the parent of V. So, as a consequence of split operation, a new overflow has occurred at the parent U of V, which has to be fixed. So, you again have to perform the split operation. So, again perform split operation. So, a new node, root is created, which is 120, and 120 is stored there. You split the node which there is an overflow as V prime. So, this will be V prime, this will be V double prime. V prime will save K1, K2, V double prime will save K4, the new root will save or will hold K3. So, in the worst case, this gets propagated all the way up to the root where it is finally resolved. So, we see that insertion can lead to violation in size property, and we use split operations to resolve this violation. As a consequence, it might happen that there is an overflow at the parent U of V. In the worst case, we have seen it gets propagated all the way up to the root where it is finally resolved. Now, we have seen that a split operation takes a constant time, because the number of operations that you do are independent of the size of your 2-4 tree. It is all locally the rearrangements are done. So, in the worst case, insertion in a 2-4 tree will take time which is proportional to the height of the tree, which we know is log n. So, insertion in a 2-4 tree in the worst case will take logarithmic time. Next, we look at how we are going to perform the deletion or a removal operation on a 2-4 tree. So, again, as we normally do in a binary search tree, to remove an item or a key from a binary search tree, first we search for the key. So, suppose in the given 2-4 tree we want to delete the key 4. Now, for deleting 4, we will first search for 4. In this particular case, the 4 happens to be at the leaf node. it might happen that suppose we wanted to delete say 5 or say 12, which is an internal node. 4 we have seen is an internal node whose all children are external nodes. So, that is a special case. If you recollect, binary search tree also had this special case where the leaf that the node that you want to delete is a node at the last level, then we can simply delete it. Otherwise, you have to find the successor and deal with the successor of the key that you want to delete. So, removing an item, we can always be reduced to the case where the item to be removed is stored at a node V whose children are external nodes. Like in binary search tree, this also can be done by a procedure which is similar to finding a successor in a binary search tree. So, suppose that item that we want to delete is the ith atom in a node Z that has only internal node as its children. We find the rightmost internal node in the subtree rooted at the ith child, so that the children of V are all external nodes. We swap the item to be deleted from Z with the last item of V and delete that item from the tree. Before illustrating this, let us try to understand how the deletion is going to be handled. So, essentially what we have seen is removing an item essentially means removing an item or a key from the external node of V. So, as we delete 4, we see that 4 becomes a one node, that is it has one children, and so it is not holding any value or not holding any key. That violates the size property of the 2,4 tree. A 2,4 tree, every node has to be at least a 2 node. So, a 1 node is not allowed in a 2,4 tree. Such a situation, we say an underflow has occurred. So, the underflow has to be resolved. Now, for resolving underflow, which has occurred at this particular node where 4 was present and is deleted, we check whether there is an immediate sibling which is either a 3 node or a 4 node. So, in this case, underflow has occurred at this node, it has a right sibling which is a 3 node. In such case, we perform what is called a transfer operation. Under transfer operation, we move a child of W to V. So, under the transfer operation, V was the node that has been deleted, W is the right sibling, we move a child of W. So, W here had 3 children, we move one of its children to a children of V. We also move a key from W to the parent of U. So, we move 6, which is a key in W, to the parent of V, which is here. So, 6 is moved here and a key from the parent is moved to V, correct. So, under the transfer operation, we move a child of W to V, a key of W to parent of U, parent U of V, and a key of U to V, right. So, if you observe here, so this is V, this is U, this is W. So, this is V, this is W, this is the parent of V, which is U. So, under this we are going to transfer one sibling from the right sibling, one child to the child of V. We move a key from here to the parent at which the underflow has occurred. So, 6 is moved upstairs to the parent of this, and 5 is moved to the node where the underflow has occurred. So, this is precisely a transfer operation. So, once we do the transfer operation, the resultant tree is a 2,4 tree. Now let us look at the other case, that is node at which the underflow has occurred does not have an immediate sibling which is a 3 node or a 4 node. Let us look at a case where we want to delete a key which is present in a node whose children are also internal nodes. So, let us try to delete 12 from the 2,4 tree. Now, 12 as we have seen, as we have said, is present in a node which is an internal node and whose children are also internal nodes. So, we look at the rightmost internal node in the subtree rooted at the ith child. So, 12 is the first key. So, at the first child of Z, such that all other so that the children of V are all external nodes. So, we look at 12. So, this is the first key. So, we look at the first child and a subtree rooted at this, and look at the rightmost node. The rightmost node is here. We swap 12 and 11. So, we are going to swap 12. So, these keys are going to be swapped. So, 11 will come here and 12 will go there, and we will delete 12 from the tree. So, as we have said, essentially we can always reduce to a case where the item to be removed is stored at a node whose children are all external nodes. After we perform this operation, we have seen that, so 11 has come here and 12 which was swapped and had come at this particular node has been deleted. So, there is a underflow at this particular point. So, what we have here is a underflow. Which has to be resolved. Now, unlike the first case when we deleted 4 from the tree, the node which is where the underflow has occurred has no sibling, immediate sibling, which is a 3 node or a 4 node. So, we have only one sibling, or its immediate nodes are not 3 or 4 nodes. We perform what is called a fusion operation, in which we merge V with a sibling, create a new node V prime and move a key from parent of V to V prime. So, in this case what we do is we merge. So, there is a merge operation. So, these two particular nodes are merged into a single node, and so this will have 3 children 1, 2 and 3. We move a key from the parent to this merged node. So, 10 will move here. So, if we have only one sibling, or if the immediate siblings are 2 nodes, we merge V with a sibling, creating a new node V prime and move a key from parent U of V to V prime. So, after the fusion is done, it might resolve the underflow, or underflow will get propagated one level up. So, like transfer operation, the fusion operation also may cause a new underflow to occur at the parent. In this particular example, it resolves the underflow. In the worst case, this can get propagated all the way up to the root, where it is finally resolved. So, again like insertion, deletion will also take time proportional to the height of the 2,4 tree. Deletion would involve first searching, which we know will take log n time. Then it will take either a transfer or a fusion, which takes a constant time, and at the most underflow can get propagated right up to the root of the tree. We know the height of a tree of a 2,4 tree is order log n. So, this can at the most again take time of the order log n. So, the complete time taken by deletion as in insertion will be of order log n. Thank you.